In our last presentation, we found out how to find the angle y of t given the trolley having a trapezoidal acceleration profile. And we talked about how the issue was now to pick t1, t2, and t3 so that we go the desired distance but have no sway at the end. In this presentation, we'll solve the problem. As it turns out, there's more than one way to do this. Our first step will be to simplify the expression on the previous page. We'll notice that all the 1's cancel each other out. So the expression now will have a few less terms. The next thing we'll do is we'll choose t1, t2, and t3 so that we get some of these terms to cancel each other out. Specifically, we'll have the terms circled in green cancel each other, and the terms circled in blue cancel each other. So we have to pick t2 such that minus cosine square root of g over L t cancels plus cosine square root of g over L t minus t2. And we'll have to pick t1 and t3 such that cosine square root of g over L t minus t1 will cancel minus cosine square root of g over L t minus t3. These desired cancellations are indicated here by the equations labeled star and double star. Clearly, for the star equation to be true, t2 must be an integer multiple of 1 period. Therefore, t2 has to be equal to m 2 pi over the square root of g over L. We noted before that 2 pi over the square root of g over L was a period of oscillation. M here is an integer. If we choose t2 in this fashion, cosine of square root of g over L t minus t2 will be equal to cosine of square root of g over L t, and therefore equation star will hold. So now we've satisfied one of the cancellation conditions that we desired. Let's now take a look at the other condition. For equation double star to hold, we must have the following. t3 minus t1 equals n times 2 pi over square root of g over L, where n is an integer. You notice this condition is just like the one we had before. That is, the difference between t3 and t1 needed to be an integer multiple of periods. Before we developed the relationships between t acceleration, t coast, t1, and t2, and they were t1 was equal to t accel, t2 was t accel plus t coast, and t3 was t accel plus t coast plus t accel. You'll now note that t3 minus t1 is equal to t accel plus t coast, which is equal to t2. So the expression we have at the top of the page here says that t2 must be an integer number of periods. But we already knew that from condition star. It also said that t2 had to be an integer number of periods. So equation double star does not really tell us anything different than equation star. It's not a separate condition. It in fact is the same condition. Now you should remember that t2 is equal to t acceleration plus t coast. So we have this result. T acceleration plus t coast equals m times 2 pi over square root of g over L. That is the condition for y of t to be 0 for all t greater than t3. That is the condition where the load has no sway after the trolley has stopped. I'd like you to think for a moment about this condition. First, we don't know m yet. We do know it's an integer, but we still have to pick it. Second, this is one equation in two unknowns, t acceleration and t coast. So even if we have picked m, we need some way of deciding what values of t acceleration and t coast to pick amongst all those that satisfy this equation. we do have another equation. It is the distance we desire the trolley to go. The equation was d equals a times txl times the quantity txl plus tcoast. We had found that txl plus tcoast was equal to m times 2 pi over the square root of g over L. We can substitute that into the above expression, and we'll find the distance is equal to a times txl times m times 2 pi over square root of g over L. Solving this expression for txl, we find txl equals d over a times square root of g over L divided by 2 pi m. Now since txl plus tcoast is equal to m times 2 pi over the square root of g over L, we can solve for tcoast. And tcoast is equal to m times 2 pi over the square root of g over L minus d over a times square root of g over L divided by 2 pi m. You'll notice that m is showing up in the numerator of the first term and denominator of the second term. Now, we still don't know what this integer is, and we could choose various values for it, but some values clearly don't make sense. tcoast cannot be negative. It must be greater than or equal to 0. If we change the expression for tcoast to an inequality, we'll find that m must be greater than square root of d over a times square root of g over L divided by 2 pi. If m is not chosen to be larger than this number, we will have tcoast to be negative, and our answer will be nonsensical. But we can choose any value of m as long as it's larger than this number. If we want to move the trolley as quickly as possible from the start position to the stop position, we'll want to use the maximum acceleration of the trolley, which will be specified by the motor torque. We designate this maximum acceleration Amax, and given that, we then can find the minimum value of m that may be used. M minimum will be equal to the Ceil function of the quantity square root of d over Amax times square root of g over L divided by 2 pi, where Ceil is the MATLAB command that rounds up to the nearest integer. If we pick m greater than this m min, we can then solve for t acceleration and t coast using the expressions that we had before. So this gives us an algorithm for picking the timing such that we have no sway after the trolley has come to a stop. We pick m as an integer greater than m min, and then solve for t acceleration and t coast from these expressions. Should one choose m to be m min, or should one choose it to be a larger value? My analysis has shown that solutions of this form will arrive soonest at the final position if m is chosen as m min. To close this presentation, we'll look at a simulation where the timing has been chosen in this optimal fashion. I hope you now see the power of the techniques we've been developing in this class to solve difficult and complex problems. To arrive at this solution, we have employed many of the ideas that we have developed, including linearity, time invariance, Laplace transform, unit steps, and delays. Let's now look at the simulation. As before, the distance traveled will be 37 meters, and the acceleration will be 0.5 meters per second squared. For this simulation, m was chosen as m min, which was 2. With this value, the total time to complete the translation was 18.5 seconds. In the simulation, this is sped up. You'll note that when the trolley stops, the load will have no sway. We'll now run the simulation again, but this time we'll choose m equals 3. With this value, we'll find the total travel time will be 22.9 seconds. No sway is achieved when the trolley comes to a stop. You'll note the time required to complete the motion was considerably larger when m was chosen greater than m min.